Alright, and welcome to the second part of our 28th lecture for multivariate calculus. This is my third shot at recording this properly. I keep catching fatal typos and mistakes that I've made, and I can't just scribble things out and correct them on the fly like I used to do in lecture. That's part of why all of this is taking me so much longer, and part of why I'm just a bit behind at this point on getting lectures posted. But we are going to attempt to get caught up with having lectures posted, certainly by the beginning of next week. And there's also a big stack of grading left to do, including your exams, and I will get to that as quickly as I can, folks. So, the plan for the second part of today's lecture is to continue practicing some triple integrals. So just as in the last part, I'm going to be throwing integrals at you, and you can proceed in whatever way seems best to you. So for our first such sample problem, let's consider the region which lies inside the cylinder given by x squared plus y squared equals to 1, and the sphere given by x squared plus y squared plus z squared equals to 4. So take these two regions and take these two surfaces and consider the region which lies inside both of them. And I want you to find for me the volume of that region. So again, go ahead and pause the video, give that some thought, and we will discuss it momentarily. Alright, so the first thing I'm going to do is draw this region. So the cylinder x squared plus y squared equals to 1, that is a cylinder having the z-axis as its central axis and also having radius 1. And I've sketched it here. It would have infinite volume itself. The cylinder has infinite volume. It extends infinitely in both directions. But we only want the portion of that cylinder which also lies within the sphere of radius 2 centered at the origin, which I've also sketched to the best of my ability here. So we want the region that's inside the cylinder and also inside the sphere. So this is like taking the sphere, for instance, and boring out a column from it and removing that column and considering the volume of that column that you have bored out, the way that they take ice sample cores when they're studying climate change. So in cross-section, it's going to look like this. We've got the cylindrical walls here, and then you've got these spherical caps. The bottom part of the sphere here is the lower cap, and the upper part of the sphere is the upper cap. So if we wanted to, we are going to proceed in cylindrical. Cylindrical seems like the most natural way to represent this region. In my horizontal plane in cross-section, it's just going to look like a disk. So that indicates to me that it should be the xy plane that I allow to be represented by r and theta. So we're going to take cylindrical as polar plus a z here. And in the r theta plane, we're going to be looking at theta going from 0 to 2 pi and r going from 0 to 1. That gives me the unit disk centered at the origin in the r theta plane. And then for my z variable, z is going to be going from the lower portion of the sphere down here all the way up to the upper portion of the sphere, the upper little spherical cap on my cylinder. And the equation for the sphere, if you solve for the lower half of the sphere in Cartesian, you would get z equal to the opposite of the square root of 4 minus x squared minus y squared, but minus x squared minus y squared is minus r squared once the xy plane is converted into the r theta plane. So this equation gives me the lower half of the sphere in cylindrical coordinates, and this equation likewise gives me the upper half of that sphere in cylindrical coordinates. So we want all the points in the unit disk centered at the origin, and for each such r theta pair, we're going to be letting z go from the lower sphere to the upper sphere. And if I do that for all such r theta pairs, I'll be able to describe the whole of this region. We have been asked to find the volume of this region. So to find the volume of this region, we'll take the triple integral of integrand 1 across the region. As we have represented the region in cylindrical coordinates, the triple integral of integrand 1 is going to become an iterated integral. Our integrand is going to pick up a factor of r because the dv expression is r dz dr d theta in cylindrical. The bounds for z are from the lower sphere to the upper sphere with it expressed in cylindrical. The bounds from r, for r, r, 0 to 1, and the bounds for theta is 0 to 2 pi. So our first integral does have variable bounds. We're not able to factor this out yet. If we integrate with respect to z, we're going to get z times r. If we plug in the upper limit of integration and then subtract off the value of the antiderivative at the lower limit of integration, we're going to end up with 2 times r times this square root. Now the remaining two integrals do have constant limits of integration, and I'm able to write the integrand as a product of a function of just r, that being the whole integrand here, and a function of theta, that being 1. So I'm going to factor this double integral into the product of two single integrals. This one's trivial. This one is a straightforward application of u substitution. I give my choice of u here together with the du term, and we can proceed and solve. At this point, I'm plugging in the limits of integration, and I'm choosing not to simplify further. I could go a bit further. 4 to the 1/2 is 2. 2 cubed is 8. So I could write this as 3 to the 3 over 2 minus 8 if I chose. But this is fine. So that is the volume of the region contained inside both of the sphere of radius 2 centered at the origin and the given cylinder. For our next problem, I'm just going to hand you this iterated triple integral and ask you to solve it. So go ahead and pause the video, give that some thought, and we will discuss it presently. Alright, so let's give this a try. If you just try to proceed straight away, you can find the first antiderivative certainly. My integrand is 1. I take an antiderivative with respect to z and get z, and I can plug in my upper limit and subtract off the value of my lower limit. You should end up with integrand just equal to the square root of 9 minus x squared minus y squared. You're going to have minus a negative, so you just get the root here. And then when you try to integrate that with respect to y, you should not be able to. It does not integrate well. So maybe a different coordinate system will be useful. In order to explore that possibility, I'm going to use the limits of integration that have been handed to me. I am going to use them to reconstruct the geometric region that I'm integrating over, and then I'm going to have a look at that region and decide which coordinate system seems to be a best fit for representing that region. And when I go to try to reconstruct the region based on the limits of integration, I'm going to do that going from the easiest aspect of this, or the easiest part to think about, to the harder parts. So which of my variables has the simplest limits of integration? That's always going to be the outermost integral. The outermost integral has to have constant limits of integration, and that's a very nice and simple place to start with your attempt at reconstructing the region from these limits. So my outermost integral here is with respect to x, and the limits of integration are -3 to 0. So on the x-axis, x is going from -3 and sliding over towards 0. That's simple enough. For each such value of x, I then have y going from y equal to 0 to y equal to this square root expression. In the xy plane, y equal to 0 represents the x-axis. So we'll have y going from the x-axis up to, and this expression, if you square both sides and rearrange it, you'll see the equation for a circle of radius 3 centered at the origin. Because y is set equal to the positive square root, we know that that means that we're only looking at y going to some portion of the upper half of that circle of radius 3. So square roots always return a positive. With y equal to this square root, we're only going to be seeing positive values of y here. So y is going from y equal to 0, the x-axis, up to this portion of the upper half of the circle of radius 3 centered at the origin. So now I have this picture in place, and already it's looking like Cartesian was probably not the best choice to begin with here. And we will then think about the limits of integration for our final variable, the z variable. Those are given as this negative square root and then 0. So just as before, if I square both sides of this lower inequality, of the left-hand inequality here, I can recover the equation for a sphere of radius 3 centered at the origin. With z set equal to the negative square root, we know that we are talking about a portion of the lower half of that sphere. So z is going from some portion of the lower half of the sphere of radius 3 centered at the origin up to the surface z equal to 0, which in 3 space is the xy plane. So now we have a picture which I'm rather proud of, as it's one of my better pictures this term. We are looking at this lower northwestern eighth of the ball of radius 3 centered at the origin. We had this picture, that's the upper surface here, the upper region in the xy plane is the drawing that we've done there. And for each such value in the xy plane, we have z going from the lower surface, this portion of the sphere, up to the upper surface, this portion here of the xy plane. So this is the region that we're dealing with. This is the region we've been asked to integrate over, and because it is an eighth of a sphere, it's like somebody took a ball, not a sphere rather, but a ball. Somebody took the ball, they lopped off the top half and tossed it, and then they quartered the bottom half. And we're looking at the northwestern corner of that lower portion of the sphere. I say northwestern because we're dealing with negative x values, which is like the west, and positive y values, which I tend to think of as north. So, because it is a fraction of a sphere, spherical coordinates are going to be the most natural way to represent this region. In spherical coordinates, I want rho going from 0 to 3. That gives me the ball of radius 3. But then I'm going to specify that I only want this portion of it by limiting the values for my angular variables. So looking in the xy plane here, we can see that we want theta. Theta starts at the positive x-axis for theta equal to 0. Our region doesn't start until theta has rotated up to a vertical position at pi over 2. Theta equal to pi over 2. And then the region continues as theta rotates from pi over 2 down to theta equal to pi. And that's the largest value of theta associated with this region. Recall again that theta equal to pi over 2 is the positive y-axis. Theta equal to theta equal to pi gives us the negative x-axis. And so it's between the positive y and the negative x-axis that we're seeing the region itself, and those are my bounds for theta given here. Also recall that phi between 0 and pi over 2 gives us the upper half of 3 space, and phi between pi over 2, the xy plane, and pi, the negative z-axis, gives us the lower half of this region, of 3 space, I should say. And so phi begins to drop from its vertical position. My region does not begin until I arrive at phi equal to pi over 2 in the horizontal plane, and the region continues through all values of phi up to and including phi equal to pi. So we've got phi going from pi over 2 to pi to give us the lower half. This equation tells us that we're dealing with the lower half of the ball, and this equation tells us that we're dealing with just the northwestern corner of that lower half, whereas this equation gives us the original ball itself. So we have constant limits of integration, where we began with an equation with somewhat nasty looking limits of integration. When we re-represent this region in spherical, we are going to end up with constant limits for each of our integrals, meaning that this region is actually a rectangular box in spherical coordinates. We do complicate the integrand a bit. We introduce a rho squared sine of phi expression into the integrand, and that is the price we pay for simplifying the limits of integration. And ultimately, the price is not too steep. We have turned a problem that was impossible in Cartesian into a very simple problem in spherical. In particular, with all of our limits of integration being constant, and our integrand being given as a product of 3 functions, one just depending on rho, one just depending on phi, and an implicit function of 1 depending just on theta, we can factor the iterated triple integral into the product of 3 single integrals, and they are all relatively easy to compute, and we get 9/2 pi. So that's our final answer, and we had to achieve it by translating an integral that we were handed in Cartesian coordinates into an equivalent integral in spherical coordinates. Next question. We have a formula for the volume of a sphere of a given radius. So if you take a sphere of radius r0, it's fairly well known that the volume of such a sphere is 4/3 pi r0 cubed. I want you to prove that this is the volume of a sphere of radius r0 using the techniques that we've developed in multivariate calculus. I say prove, it's not a proof, it is a proof, but it's not something that you need proof theory for. I could reword it and say, consider a sphere of radius r0, show that its volume is equal to 4/3 pi r0 cubed. And so that's what I'm asking of you. Use the techniques of multivariate calculus to do this thing. So give that some thought, and we will have a look at a solution momentarily. Alright, so I'm going to call our region S for sphere, and I'm going to let it be centered at the origin. The volume of a sphere does not change if you move it about in 3 space. As long as it has the same radius, the volume is going to be the same value. So for convenience's sake, I'm going to take this sphere and I'm going to set its center at the origin. That's going to make it easiest to represent this region in spherical coordinates. So a sphere of radius r0 centered at the origin is going to be given in spherical coordinates by 0 less than or equal to rho less than or equal to r0. Really, that's all you would have to say if you wanted to characterize the region, but we'll go ahead and give the limits or the bounds for theta and phi so that we have them here on hand and can plug them in as our limits of integration for the respective integrals. So 0 less than or equal to r0 less than or sorry, 0 less than or equal to rho less than or equal to r naught, that is the ball of radius r naught, centered at the origin. We are not placing restrictions on theta, so theta gets its full 0 to 2 pi range of motion, as does phi, going from 0 to pi. It gets its full range of motion as well. So we're not just looking at some portion of the sphere, we're looking at the whole sphere, which is why we have the full range of values for both of our angular variables. Now we know that the volume of the sphere will be the triple integral of constant integrand 1 over the sphere, and I can write that triple integral as an iterated integral in spherical coordinates. I introduce a rho squared sine of phi term into my integrand as part of the dv expression. My bounds for rho are 0 to r naught, for theta 0 to 2 pi, and for phi 0 to pi, just as stated above. This is a very simple integral. It is again the simplest possible integrand and constant limits of integration for each of our variables. We can solve each of them here in a simple way, and we get our 4/3 pi r naught cubed. I love problems like this. I love it when there's a fact that you were maybe taught in grade school and just made to memorize, and now that you have more sophisticated mathematical techniques, you can actually see where it comes from. You can derive it. Sometimes if I've forgotten formulas of this type, I will challenge myself to re-derive them rather than look them up, as long as I can do it quickly enough, of course. But I like this. I like the fact that the math sort of, some lower level math unlocks and becomes trivial once we get into some higher level math. As a final sample problem, let's consider a tetrahedron. So this would be a object that has 4 vertices, a geometric object with 4 vertices and flat sides in some sense. And I want you to consider a tetrahedron with these 4 vertices, and I want you to find its volume. So tetrahedrons are like, sort of like pyramids in a sense. They're not exactly like the pyramids in Giza because those have square bases. But if you took a pyramid like the pyramids in Giza, Egypt, and you made one with a triangular base, that would be a tetrahedron. It's got flat sides and it's got 4 vertices or 4 corners in it. So consider the tetrahedron with these 4 vertices and find its volume. So give that some thought, work on it, try to solve it in any way that seems appropriate, and we will have a look at a solution momentarily. And that moment has come. Let's take a look at a solution. So first thing I'm going to do is draw it. We had the origin as one of our vertices. I'm drawing this with the origin as like a back corner, so this is like you're looking down into the corner of your room. Here's the positive x-axis and the point 200. Here's the positive y-axis and the point 020. And here's the positive z-axis with the point 002 as the vertex. And then back further into the page is the origin there. So this is our tetrahedron. It's got 3 sides, which are right triangles, that being the one in the xy plane, the one in the xz plane, and the face in the yz plane. And then there's this front tetrahedron, which looks like an equilateral triangle here. And we're actually going to find this volume by taking a double integral, not a triple integral. So formally, this is supposed to be practice for triple integrals, and had we not lost a week to the coronavirus, we would have covered a method. These are the type 1, 2, and 3 integrals for triple integrals, type 1, 2, and 3 regions for triple integrals. We would have covered that method, which would have allowed us to compute the volume of this region as a triple integral. But we did lose that time. We cut that subtopic out. And so we still have a means to compute the volume of this region as a double integral. It's a little bit of a trick question because we've been talking about practicing triple integrals, and now I'm throwing at you a problem that has to be computed in a double integral. But it is in keeping with the spirit of today's practice problems, which is, you don't encounter problems generally under some subheading so that you know what technique is needed for the problem. If you're either out in the wild working on problems and using math, or if you're taking an exam, you're just going to see problems, and you're not going to be able to think like, oh, so this problem's coming up in the section on cylindrical coordinates, I probably need to use cylindrical coordinates. Instead, you just encounter the problem without context necessarily, or without at least the mathematical context of how the problem would be solved, and you have to decide which techniques are appropriate. So, this is a bit of a trick question because you actually need a double integral. We have a theorem when we study double integrals that said if you want the volume of a region that lies above some portion of the xy plane and below some non-negative surface, you integrate across that region of the xy plane, and your integrand should be the equation for that surface, and that will give you such a volume. So we're going to use that theorem. We're going to think about what does this region look like in the xy plane, what surface is the upper bound for that region, And how do we integrate across that region of the xy plane, and what is the equation for that surface, which is to become our integrand. So doing the easy part first, in the xy plane, we are looking at this right triangle here that I see as the base of my region. If I draw that in the xy plane, here's point 2, 0. That used to be 2, 0, 0, and we thought about it as a point in 3 space. Here's 0, 2. That's 0, 2, 0, and considered as a point in 3 space. And here, of course, is the origin. So you could represent this as either a type 1 or a type 2 region. I tend to default to type 1 because I think about x first and then y if there's no reason to do otherwise. So x here is going from 0 to 2. That's my interval on the x-axis. For every such value of x, y is going from the x-axis up to this line. The x-axis in the xy plane is y equal to 0. And at this line, it's fairly easy to see that it is the line 2 minus x. I say it's fairly easy after having scratched out a mistake that I made, so do as I say, not as I do. But this is a line that has slope -1 and y-intercept at 2. So 0 less than or equal to y less than or equal to 2 minus x. This is a representation of the base of my tetrahedron as a type 1 region. We also needed an equation for the upper surface. The upper surface here is going to be this equilateral triangle, this plane which intersects the z, x, and y axes at the indicated points, and it is the upper bound, right? These two side walls are fully vertical. We've got this base, and then this fourth surface involved in the tetrahedron is going to be the upper bound on the region that we are trying to find the volume of. So we need an equation for that upper surface. That is to say, we need an equation for a plane containing these 3 points. And this is something that we learned to do back when we were considering planes and cross products. We know that to find an equation for a plane, you need a point that lies in the plane, and you also need a vector normal to that plane. I have 3 points lying in this plane. I can use those 3 points to construct 2 vectors. I can take the cross product of those 2 vectors to get a third vector which is perpendicular to both, and hence perpendicular to the plane. So I'm going to label my points this way, P1, P2, and P0. I did that because I'm thinking of this as like starting here and going down this branch, and starting here and going down this branch. Those are the 2 vectors I came up with. You could label them differently. You could rearrange things here. There's some possible divergence in the paths that we may take, you and I, as we go from this point to finding our actual equation for the plane. But whatever you do, you should end up with a normal vector which is parallel to the vector, or the normal vector, which I find in the end. So that will give you a way to check whether or not you do this exactly as I have done. So this is my P0, my P1, and my P2. V1 is going to be the vector that goes from P0 to P1. And remember, you always do destination minus the origin here. And so I get this vector running from P0 to P1. I get this vector running from P0 to P2. I let n be the cross product of those 2 vectors. You can review our section on taking cross products if you like, but I end up with the vector 4, 4, 4. 4, 4, 4 is normal to the plane that I'm interested in, but it's a little bit silly to have these 4s floating around. I'm actually going to multiply this through by 1/4. That will change the length of this vector, but not the direction, and I'll arrive at the vector n2, which is 1, 1, 1. These 2 vectors are parallel, so since this one is perpendicular to the plane, this one must also be perpendicular to the plane that I'm interested in. And that's the normal vector I'll use. And it looks like I'm grabbing point 2, 0, 0 to be my representative point, my x0, y0, and z0 point in the plane. And the equation for the plane is then given by this equation. I'm going to solve this for z, so the minus zeros are going to drop off. I'm going to rearrange some stuff and solve for z. And I get z equal to minus x minus y plus 2. That's believable because when y is 0, this hits 0 when x equals 2, so at the point 2, 0, 0. When x is 0, so you're on the y-axis, then, or in the yz plane, then this plane hits the z equal to 0 point when y equals 2 as well. So we can see it kind of pinning down at those 2 corners the way it should, and it looks like a reasonable expression for that upper surface. That's now going to be our integrand in the double integral that gives us the volume of this region. So the volume of the region we've been asked to find is going to be a double integral over the base. These limits of integration are given by my expression of the base surface of this tetrahedron as a type 1 region, and my integrand is the upper surface, the upper bound. So again, we have a theorem that says to find the volume between a region of the xy plane and some non-negative surface, you integrate the equation for that surface over that region. And that's exactly what I'm doing here. And this is just a polynomial, everything's relatively straightforward. So I take an antiderivative with respect to y, I plug in my limits of integration, I FOIL some stuff out and I simplify things, I collect my like terms to make my life easier, collect like terms to make life easier. This is about as simple as a type or a Calc 2 integral ever gets, a polynomial between constant limits of integration. I take an antiderivative and I come up with a answer. The last time I recorded this lecture, just a few minutes ago, I ended up with a negative here. I had made a mistake and had an incorrect term in my FOILed expression. And so I realized that it couldn't be negative if it was supposed to be a physical volume. I can think about what this tetrahedron shape is. It's got some volume. It's not a negative number. And so I got to go back and re-record the whole lecture because there was a fatal typo right at the end of it, which is unfortunate. But it does illustrate that there are sanity checks of that type. It's good to bear in mind what the big picture is. I wish I had caught that before I'd actually recorded the whole lecture. I wish I caught it when I was writing up the notes. But it is what it is. We now have the actual volume of this tetrahedron. Alright, so that will wrap up this discussion of some practice problems for triple integrals and even a double integral thrown in. And we will next time, for another lecture which I'm going to endeavor to get posted today, we will wrap up this consideration of multivariate calculus or multivariable integrals by thinking very briefly about a very general and important theorem called the change of variables theorem. So we're going to think about that just a little bit. It's going to give us some insight at least into where the expressions like r dr d theta or rho squared sine of phi d rho d theta d phi, where those extra factors that get introduced into our integrand, where do they come from and how are they analogous to some stuff that we've done before. So we're going to do that very quickly, and then we are going to move towards thinking about the last topic of our course, which is vector calculus. So we'll do that in our next lecture. I thank you folks for your attention. I will speak with you again shortly.